Good morning. This is the Chapter 6 test. Let's look at number 1 here. So we need to sketch the region enclosed by these curves and find its area. So to do a quick sketch, I'm just going to draw my axes. So x equals 2y squared. That's going to be a parabola that faces sideways here. And then x equals 4 plus y squared. So that's going to be shifted over, say 4 units. And it's going to be a wider parabola. Looks a little bit like this. Okay, so where those connect, that's our region right here. Now you could set the two equations equal to see, well, what are these points where they cross? So where is 2y squared equal to 4 plus y squared? Well, that's when y is equal to 2. So these points would be here, would be y is 2, so x would be 8. And y is negative 2. X is still 8. Great, so now we need to find the area of this. So I have a few ways of setting this one up, but I'm going to look at them. The integral, kind of like turn your head sideways. If I did this in terms of dy, then the integral would find the area beneath the curve here. So if I would do the integral for the dy, how high is it here? Well, it's going to be the bigger of the two shapes, so that dot is on the 4 plus y squared. That'd be this whole length. I want to subtract off this little length so I have just the area inside. Well, that little length I'm subtracting off is the 2y squared. And the y is going to go from negative 2 to 2. So there's our integral. We could take that. There's other ways you could have thought about this one too if you wanted to switch the x's and the y's to make it easier for you. By symmetry, you're going to get the same answer if you did everything in terms of dy dx. So anyways, let's just solve this. So negative 2 to 2. 4 minus y squared dy is equal to 4y minus y cubed over 3. We need to plug in these two values, negative 2 and 2. So when I plug in the 2, I'd have 8 minus 8 thirds. Subtract off, when I plug in the negative, negative 8 plus 8 thirds. So this is going to be 16 minus 16 thirds, which is 32 thirds. Find the volume attained by rotating the region bounded by the given curve around the specified line. So let's just sketch it. So x is going to be positive, greater than or equal to 0. So I'm only going to do the x cubed over here on this part. You know, it does look like that, but we can ignore the negative x values right now. And then y equals x is a straight line here. And so this is the region that we're going to be rotating around the x-axis. So you can sort of imagine what that would look like, sort of like a tulip opening up, whatever you want to call it. Now, we always have these choices. Do we want to do washer or shell? In this case, I'm going to go with the washer. So what that means is I'm going to draw my rectangle in there with a short side with a dx. Now, the length of this radius, that big R, I'm going to call it a radius because we're rotating it, is just your x. So the area of the circle made with that would be pi x squared. Then I'm going to subtract off the hole in the middle. That's radius is x cubed, so the area of that hole would be pi x cubed squared. And then your x values go from 0 to 1. So we're just going to solve this real quick here. So let's simplify. I'll bring the pi out in front maybe. X squared minus x to the 6th dx. which you could simplify to being pi 4/21. Those are volume units. All right, number 3. Very similar, but we're going to go about the y-axis. So we still have the x cubed thing. I'm only going to need the positive part. X equals 1, x equals 3, y equals 0. So this is my region right here. And we're going to rotate that about the y-axis. I'm going to go ahead and use shell this time just so I can keep it with dx. Because these vertical rectangles are nice because the top always hits the curve. If I used horizontal rectangles, it would be different down here than up top. So if I were using the shell method, what I'm thinking about it there is I have the integral in terms of dx. 2 pi, the distance from my axis of rotation to my x value, well, that's just what we call x, so 2 pi x. And then the height of this rectangle is going to be just x cubed. And x goes from 1 to 3 in that problem. So there's your setup. Just go ahead and finish it out. Bring the 2 pi out here. We have x to the 4th dx. 1 to 3. I would even accept it just like that. I think that gives you 242/5 or so. You can simplify it further, but that's good. All right, number 4. Find the volume of the solid obtained by rotating the region about that line. All right, so let's draw it again. Very similar again. Y equals x to the 4th. That actually looks basically like a parabola. But we only need the one over on this side. So we're going to do x equals 1 as our other bound. So it's this region, and we want to rotate around the line. Do it in yellow. X equals 2. So for this problem, I'm going to go ahead and choose the shell method. So I'm going to do a vertical rectangle there. It's going to give me a dx. So the height of that rectangle is x to the 4th. We're going to go from 0 to 1. But then we have that 2 pi r. 2 pi, the radius is the distance from this to my rectangle. Well, if this part right here is always my x, and this part right here is my 2, that radius is 2 minus x. Chris, there's your setup. And you just solve it. You multiply some things out, and you should have 2 pi, 0 to 1, 2x to the 4th minus x to the 5th dx. That'd be 2 pi 2/5 minus a 6th when I plug in the 1 and the 0. And I could simplify that a little bit. I think I get pi 7/15. All right. A spring has a natural length of 2 feet. It's 2 feet long. So there's a certain amount of work done when you go from 2 to 3. So the way we found that, remember, if your force is really like your distance, so your work is your distance times your force. This one, the force is changing. So remember, the force right here is kx. That's a spring equation. And so if this is done in feet, I'm going from 2 to 3 feet is going from rest for my spring, so 0 extension to 1 foot. Kx dx, so there's a value there. I don't know what k is, so we'll just leave it in there as a constant. So we get, when I integrate that, I get x squared over 2, plug in 1, so k times a half. Work 2 is similar. I'm going 1 to 2, 1 foot of extension to 2 feet of extension, kx dx. And that's going to be k, x squared over 2, plugging in 1 and 2, which will give me, when I do that, 4 halves minus 1 half. So I get 3 halves times your k. So if I compare work 1 to work 2, it's a third as much. And that would be that. All right, a force of 5 newtons is required to hold a spring stretched 50 centimeters beyond its natural length. How much work is done in stretching it from its natural length to 75? So let's just do this. Remembering our spring equation. If we're in metric, we could find k real fast, because it's 5 newtons of force is equal to k times, well, 50 centimeters. In meters, that would be half a meter. So k is 10 for this problem. So then to find a work, we say, well, our equation, our force equation is 10x. And we want to go from rest to 75, which is 0.75, if you want to call it that, dx. So then you find that value. So for this case, that would be 5x squared, 0.75, and 0. And that would be, when you plug that in, I actually did it by hand, so I didn't use a calculator. So I just actually called it 3/4, which would give me 45/16. I'm sure there's a decimal number that you could use as well. But there you go. And that measure, or that unit, is now in joules. A 10-foot chain weighs 25 pounds and hangs down from a ceiling. So you have 10 feet long. And then what we're going to do in the second scenario is we take the lower end and we've lifted it up to the ceiling. There's a handful of ways we could think about this one that I kind of enjoy thinking it through. What you might notice is that this top 5 feet doesn't move at all, right? So we're really talking about this bottom 5 feet. One simplistic way you could think about it is you could say, well, this section of chain has been moved up that much. You say, well, how much does this section of chain weigh? This section of chain weighs, well, it's half of 25, so it's 12.5 pounds. And it moved up 5 feet. And it turns out that that's enough if you want to do it that way. It might not be obvious that that's enough, just because, so what was that? That would be 62.5. So that would be, I wrote force, that should be a work. Just because this chain also does a rotation. So if you're not convinced by that, well, stay tuned for the next video because we're at time. I can show you another way of thinking about that.